Okay, so here I've got, let me get that on screen a little bit better. A function, the x component is sine of t, and the y component is sine of the quantity t plus 1. Okay, so what sort of shape how would you describe this shape?
It's like an ellipse.
Okay, how would you describe it?
Yeah, it's an ellipse. I guess kind of a tilted ellipse.
Okay, yeah, tilted, but an ellipse. All right, what would you say about the velocity vector here?
Well,
It seems like it's not going that fast. It's kind of speeds up over the long side of the ellipse, but then kind of slows down again.
All right.
it slows down. I guess you kind of it's slow here, and then turns around and speeds up, and then slows down as it turns, and then speeds up.
Okay, so let me turn that on. And you can, here's the velocity vector. Oops. I turned it on and then I turned it off. Let's go back to the beginning. Okay.
So
Here's
first slow, and then it gets bigger.
Slightly faster.
And then
Slows down again.
And gets bigger.
Oh, you know what? Actually, I made a mistake just setting this up. I want these to be the actual size to show the effect. So I'm going to make instead of, I was dividing them by 2 just to keep them on screen, the velocity and acceleration, but I just remembered that I don't want to divide them by 2. I want them to be their actual size. Okay, so here you go.
Right. So I guess in the actual size, the speed our velocity doesn't look like it's changing all that much, but it does slow down a little bit at the corners.
Okay. Now my real question here for you is, where do you think the acceleration vector is? Let's stop it at some point. No, just random place to stop. Where do you think the acceleration vector is here?
So I think it's kind of being.
Got your pen.
Let's see, it's right here.
All right.
So I think it's kind of being pulled maybe this way.
All right. How about you?
Yeah, because it's maybe this way and then slightly down because it wants to go kind of this way and then kind of back up again.
Okay. So let me just show you where it is.
Kind of where we thought.
That way.
Just it's a little bit less.
Okay. So I'm going to play it for a little while longer. I don't know. Just tell me where to stop it.
How about here?
Okay. Where do you think this is being accelerated here?
So I think we're being pulled, I guess, kind of maybe like up this way.
Okay. How about you?
I would say this way and a little up because you want it to go, and then this way and then back up. So yeah.
All right, so I'm going to let it play. And so tell me what you notice here.
Well, the acceleration, it's always, the end point is always at the origin.
Okay, that's interesting. So we've got something here moving in an ellipse. And the acceleration is always, appears to be basically, you know, the acceleration vector always seems to be pointing at the same spot. So it always seems to be pulling towards the origin. Does that remind you of anything?
I guess maybe like an orbit of a planet around a star. So you're always being pulled toward the star.
You're always, so this is basically, you know, Newtonian gravity right here.
Wow.
You've got something always being pulled towards the center. But the surprising thing is that it doesn't fall in to the center. It moves around in what kind of path?
Elliptical path.
It moves around in an elliptical path. And it goes forever in this orbit. And this is exactly what the Newtonian model for planets rotating around the sun. Well, I shouldn't say it's exactly. It's basically.
All right.
Is that pretty neat?
Yeah.
Well, there you go. All right. Hey, good work, guys. Fun example of parametric equations.